Okay, is it okay? Yeah. Okay, so sure, would you like to go introduce?
Yeah, sure. So hi everyone. Welcome to the first hybrid Origins talk. And today we welcome Cheng-Han Hsieh from Yale University to talk about his recent paper about cores and filament angular momentums in a star-forming region Orion B, right? And Cheng-Han is currently a graduate student at Yale University working with Hector Arce. I have overlapped with him for a couple of years. And Cheng-Han is really successful at ALMA proposals. And today the talk is about ALMA data that EPI. So let's hear what he has. Thanks.
Oh yeah, excuse me, before you start. So if you have any clarification question, send us chat, then I'll ask the speaker. Otherwise, you, please hold your question until the end of the talk. Thank you.
Okay. Hello everyone, and everyone on the Zoom. So I'm Cheng-Han Hsieh. I'm a grad student from Yale University. And today I'm going to talk about angular momentum in star formation, from filaments to cores. So star formation is a multi-scale problem. You have filaments at 10, 20 PC. Inside the dense filaments, you have protostatic cores. Within the cores, you have a disk at scale around 100 AU. So let me get this way. So the individual stars have angular momentum much smaller than the molecular clouds. So it is a classical problem in star formation to understand how does the angular momentum transfer from the large to small scales. Before we try to answer this question, we want to first ask, is there really a link between angular momentum of protoplanetary disk and the rotating cores? So at the core scales, the specific angular momentum is found to be comparable to that of the wide separation binaries. So on the right-hand side shows the angular momentum profile derived from 3 different sources from Pineda et al. 2019. So on the large scales, you can see the slope 1.7 is set by turbulence. At the smaller scales, the profile flattens. So this corresponds to a conserved angular momentum in cores. So why is it important? Because understand how cores obtain their initial angular momentum is important because it sets the angular momentum budget for the disk and the multiple systems. So it also affects the fragmentation process as well as the evolution of the disk. So on the right-hand side shows some beautiful ALMA images of circumstellar disk from D-Shop projects. So the recent simulation by Variant et al. 2020, they found there's no need for core rotation. So the disk angular momentum can be generated locally. So the idea is they simulate a core with a non-rotating core, and they found the rotation of the disk is generated by the asymmetry of the collapse. So the authors point out angular momentum in the stellar frame of the stellar object, which is not located in the center of the mass of the core, is not conserved due to the inertial forces. So you can have angular momentum of the disk. It's mostly coming from the non-asymmetrical collapse of the core, not from the conserving of the pre-existing angular momentum in rotating cores. So does that mean there's no link between the disk angular momentum and core angular momentum? If the disk angular momentum are generated locally, then there's no link between the small scales and the large scales. So we look at the recent observation by Corsero et al. 2017. So they use astroseismology, which is one of the most precise method to measure the inclination angles of the spin axis of the 48 stars from two old open clusters. And what is amazing is that they found a strong alignment exists between the 48 stars. And the authors conclude that the global angular momentum of the cluster forming clouds was effectively transferred to each stars. And this imprint has survived several giga years since the cluster formed. So why this is very shocking? Just think about it. You have protostellar, you have the molecular clouds that is at few parsec scales. So that's around 1 billion times larger than the stellar radius. And yet what they found is suggesting that the global angular momentum of the cluster forming clouds was effectively transferred to each stars. So that's 1 billion times order of magnitude difference in scale. So this is a very surprising and amazing result, suggesting a link between the large scale and small scale angular momentum. And so we can look at the intermediate scale. So this is the ALMA CO 2-to-1 observations towards a massive infrared dark cloud, G28. So, so this is a work done by Kohn, and he found there's a strong alignment between the protostellar outflows and the filament direction. So the outflow direction is perpendicular to the filament. So on the right-hand side shows the blue and red shows the blue shifted and red shifted CO outflow. So the outflow direction traces the disk angular momentum direction. So there's some link between the disk angular momentum with the global filament direction. So this poses some interesting questions like, do cores inherit angular momentum from the filaments? What is the link between the disk angular momentum with the larger scales? So how does the angular momentum of the rotating cores link to larger scales? So at larger scales, the angular momentum is mostly set by turbulence. And in Mizuki et al. 2019, they found the dependence of the specific angular momentum with mass can be explained by one-dimensional Kolmogorov turbulence. However, some turbulence simulations tend to underestimate the core angular momentum by a factor of 10. So Dib et al. In 2010 suggests that this difference is due to observation overestimate the true angular momentum by a factor of 10. So what they did is they compare the intrinsic angular momentum from simulation to the one that is derived from two-dimensional velocity maps. So they suggest that this difference is due to the observation overestimate the true angular momentum. However, in 2018, John suggests that this difference is mostly due to much smoother velocity field on smaller scales in the simulations, which results the turbulence to decay and the gravitational inflow to dominate. So he suggests this is due to numerical effects. So in 2019, Kuznetsova, she conducted a conservative order of magnitude estimate. So let's start, consider the largest eddies with a scale of around 1.1 parsec. So that's the size of a protostellar, typical protostellar core. So the eddies frequency follow k to a -½ that's set by the Kolmogorov turbulence with the largest eddy speed of around Mach 8 supersonic turbulence. And then she found the order of magnitude estimate angular momentum is still 1/10 below the minimum angular momentum observed in course. So she suggests that this is possibly indicating that the model of the turbulent origin for the angular momentum in course is inconsistent with observation. So currently, there are two competing theories in the initial angular momentum of course. So the first one is the turbulence origin, and the other one is the local generation. So the idea of local generation is that the angular momentum of the cores is generated locally and just comes from the gravitational interactions of the overdensities and other dense cores. So just recently, with the help of ALMA's high resolution observation, we start to find some rotating filaments. So this poses an interesting question on whether or not the initial angular momentum, of course, can be inherited from rotating filaments. So looking back, we have all the past observation studies have been focused on the angular momentum, of course. We studied from 1993, Goodman et al., to the recent study by Goodell et al. 2020. These past observation studies have been focused on the angular momentum, of course. It is important to point out that the angular momentum study on filaments is missing. So in the past, people have found a rotating filament in infrared dark cloud L-1215-1. And however, this filament is too large compared to the typical filament with width of around 0.1 pc, and it is difficult to link this filament to the star-forming cores. So, so we present the first angular momentum study in a rotating filament at few thousand AU scales. So this is the Orion belt, and this is an optical image. So on the center is the Orion B region. So you can see the two bright optical region. That's the HH 24 to 26. So there are some outflows in the north, and between the two bright region, if we look at the ALMA, cycle 4 N2D plus, there lies a very cold, dense filament. So N2D plus is a deuterium species, so it traces the cold, dense gas. So the temperature is around 10 K, the number density was 10 to the power 6 centimeters cube per centimeter cube. So we know on the upper side, there's some outflows. We also found some CO outflows in the southern side. So, so that's why we want to focus on the central region, which is more quiescent and not affected by feedbacks. So this is the system velocity map across the central filament. And we found there is a clear velocity gradient along the filament minor axis. So this is the channel maps. Let me show you the channel maps. So you can see the emission moves from left to right. So there's no velocity gradient along the filament major axis. And this is a rotating filament. So we obtain the average velocity profile across the filament, and we use it to derive the specific angular momentum profile. So we found the total specific angular momentum to be around 4 to the power 10 to the 20 centimeters cube per second, with the profile proportional to R to a 1.8, which is consistent with the profile set by turbulence. We compared the rotational energy with the gravitational energy, and we found all of these values are consistent and similar to the values found in cores of the similar size. So we want to first compare our specific angular momentum profile with what is found in cores. So on the right-hand side shows the specific angular momentum profile derived from our filament. And on the left-hand side shows the specific angular momentum profile of class 0 cores. So first of all, we can see at the larger scale, we can see our slope is 1.8, and for the cores is around 1.6. So both of these slopes are consistent with the profile set by turbulence. So we know that at larger scales, the profile is set by turbulence. But at smaller scales, we can see for the class 0 cores, around 2000 AU, there is a flattening. And however, for our filament, we do not see a flattening, which indicates a conservation of angular momentum at smaller scales. So, our observed filament shows a profile that is consistent with the profile set by turbulence, all the way down to a few hundred AU. So this is showing us that the filament and cores develop simultaneously in our Orion B filament due to the multi-scale growth bound nonlinear perturbation generated by turbulence. So why is it rotation? When you see velocity gradient across the filament, it can be due to many different things. It can be due to rotation, it can be due to inflow dominated by a central point mass, it can be due to gravitationally contracting filament. So how do we tell the difference? So the idea is to look at the slope of velocity times r. So the VR, if it's rotation with conserved angular momentum, the slope should be flat. If it's inflow dominated by the central point mass, VR should proportional to r to the power of 0.5. And however, our observed specific angular momentum profile is proportional to r to the 1.8. So we can rule out the inflow dominated by the central point mass case. As for the gravitational contracting filament, we need to first fit the density profile. So we fit the prominent profile across the filament, and then we know the inflow velocity for a gravitation contracting filament is given by the above equation. So we integrate the Palmer profile fit, which is the projected Coulomb density, to get the mass as a function of radius. And the total normalization is set by the mass of the filament, which is around 11 solar mass. So the purple.
Before you go on, we have a question in the chat from Yancy Shirley on the N2D plus, I believe. So he says, deuteration is a strong chemical fractionation process. How strongly do abundance variations along the line of sight affect your ability to measure velocity?
So N2D plus is a very optically thin tracer. So we only see the filament in N2D plus. So there's no contamination in the foreground or background. So we're very certain the velocity profile trace is tracing the filament. Any more questions?
Yes, does it answer you? Yes, we can continue.
Okay, so so we can see the gravitational contracting filament profile is very different from our data point. So we can rule out the case of gravitationally contracting filament. And we also follow Chen et al. 2020's to calculate dimensionless quantity CV, which compares the turbulence energy with the gravitational energy. So we found CV is around 0.3. So this rules out the scenario where the observed velocity gradient is due to turbulence compression. So how about the large scale info? So to look at the large scale info, we look at the more diffuse tracers such as 13CO and C18O. So here is the velocity profile for C18O. And we found there's no velocity structure in the filament region in C18O. So there is no large scale inflow towards the central filament. So one of the biggest problems for rotation is if you have magnetic fields, then magnetic braking effects can quickly slow down the rotation. And so we want to check the magnetic fields in this region. So we use the JCMT data. So on the right-hand side shows the B field direction derived from JCMT polarization. So as you can see, the magnetic field is perpendicular to the rotating axis. So the magnetic braking effect is small. And we also use the Chern-Sekar Fermi method to estimate the B field strength. So this derived B field strength is correspond to a median density region traced by C18O, and the value is around 50 mu Gauss. But for the N2D plus, it is much denser. So we scale the B field strength with density, and we found it is roughly around between 50 to 1,000 mu Gauss. There's a huge range. So we also look at the turbulence in this region, and on the right-hand side shows the N2D plus velocity dispersion map. And we found the average Mach number is around 1. So this is a transonic filament. And this is as for 13CO, this is the velocity dispersion map. And we also look at the velocity dispersion map for C18O. Again, there's no structure. So it's showing that this filament is only being traced by N2D plus. So we compare the different energies of this filament, the gravitational energy, turbulence energy, rotation energy, and magnetic field energy. And we found this filament is mostly supported by magnetic field energy, followed by turbulence, then rotation. So we found the first rotating filament at few thousand AU scales. And this rotating filament in Orion B shows has a specific angular momentum profile that is consistent with the rotation acquired from ambient turbulence. This implies the cores and their host filament develop simultaneously due to a multi-scale growth of nonlinear perturbation generated by turbulence. So this finding is very important because this gives us a unique opportunity to have the first robust test on the origin of the core initial angular momentum. So now we talk about the filament. Let's move on to the smaller scales. So the next topic that I'm going to talk about is feedbacks and the evolution of the disk core angular momentum. So in the small scales, for example, disk, the large scale process, such as the collapse of the protostellar core, determines the evolution of total mass and angular momentum of the protostar disk system. So this is the result done by the recent simulation by Xu et al. 2021 and in Princeton. So they trace the angular momentum flux through the 20 AU sphere and see what are the different major contribution from different mechanisms. So they found the dominant one is from the large scale pseudo disk as well as the collapse of the protostellar core. So collapse of the protostellar core is the dominate contribution to the injection of the angular momentum in disk. As for the removal of angular momentum in disk, so outflows can remove a significant amount of angular momentum in disk. So there's some simulations as well as observation finding outflows carrying a huge amount of angular momentum. So, however, it is important to point out there are some problems. So in observation, the biggest problem is the mass loss rate by outflow is very uncertain. So without the accurate determinant of the mass loss rate, you cannot have accurate determinant of the angular momentum, knowing how much angular momentum is removed. And for simulations, the biggest problem is it depends on the magnetic diffusivity parameter. So if you set the magnetic diffusivity parameter to be high, then the magnetic field is weaker in the central part of the disk, and it drives weaker outflow, which carries less angular momentum. So it's highly dependent on the magnetic field set up inside the disk. And for even in a series, there is a difference. There are two competing series, one from the X-wind model and the other one from the disk wind model. So the angular momentum carried by the protostellar outflows and jets are very different. The X-wind model carries much less than 10 AU per kilometers per second angular momentum. However, the disk wind model carries up to 100 AU kilometers per second angular momentum. So it is like orders of magnitude different, even in the predictions between the two series. So just another motivation. So recently, Tobin et al. 2020, they surveyed 328 protostars in Orion molecular clouds, and they found a surprising result. They found the disk radii decreases as protostar evolves. So this is at odds with the predictions of the non-magnetized model, which involves the inside-out collapse with the initial solid body rotation. And this is also at odds with the MHD models, which predict disk growth as the envelope dissipates. So the author proposed that this is due to protostellar outflows, removing a significant amount of gas, preventing the accretion of high angular momentum material, thus limiting the disk growth. So I want to focus on outflows. So outflows can directly remove the angular momentum from disk. It can also remove the significant amount of the gas and prevent the accretion of the high angular momentum loss limiting the disk growth. Outflows feedback on the protostellar core will affect the inflow accretion from the collapse of the protostellar core, and that will determine how much will affect the injection of the angular momentum. So to look at these two different aspects, first, if we want to look at how much angular momentum is directly removed from the outflow from the disk, we need to establish an accurate way to measure the mass loss rate by outflows. And if we want to look at outflows impact on the collapse of the protostellar core and how that affects the injection of angular momentum to disk, we need to understand the outflow core interactions and its implications on core collapse. So together with this, we can start to build a picture on how outflows determine the evolution of the total mass and angular momentum of the protostar disk system. So I will start with the establishing an accurate way to measure the mass loss rate by outflows. So Hector and I did a survey of 21 proto outflows in Orion A. So here shows some of our beautiful sources. The blue and red shows the blue shifted and red shifted CO outflow. And the green is the C18O, trace the central dense core. So the first row is class 0, second row class 1, the third one is the flex spectrum sources. As you can see, the outflow cavity widens with time. So with the high resolution of ALMA, we start to see very clear outflows in 13CO and C18O. So on the left-hand side shows the 13CO outflow. And on the right-hand side shows the C18O outflow. The blue and red shows the blue shifted and red shifted C18O outflow. So with the with this, we can, with the optical sinc tracers, such as 13CO and C18O, we can start to determine, to measure the mass of the outflow to very accurately. So we can, we follow the method by Dalham et al. 2014 to correct the optical opacity of CO, opacity of the CO. Okay, and also we can use the different CO isotopes to avoid saturation. So this is a mass spectrum. So we calculate the mass at different channels. So we use CO to trace the high velocity outflow wind, and then followed by 13CO and C18O as we move closer to the system velocity. And also we correct for the inclination by fitting a wide angle wind model. So a wide angle wind model has three parameters. So it's basically a theoretically symmetry parabolic shell surface, and it described by Z equals C naught R squared. So the C determines how wide the parabola opens. V naught is just the characteristic velocity, and I is the inclination angle. So we start by creating the CO mask, outflow mask from integrated intensity maps. And then we, for each C naught and inclination I pair, we fit the wide angle wind model. Then for different set of C naught and I, we generate the position velocity diagram parallel to the outflows with the characteristic velocity 0.3 all the way to 6 kilometers per second. So in the center shows the residue plot. So the blue is the wide angle wind model, and the red is the position velocity diagram of the outflow parallel to the outflow direction. So after we reduce down number of solutions, we later use the position velocity perpendicular to the outflow axis to determine the best fit parameter. So on the right-hand side, the color is the position velocity diagram perpendicular to the outflow axis, and the red shows the wide angle wind model. So the inclination correction will affect the outflow mass ejection rate by a factor of 3 to 5. So without this correction, any possible evolutionary trend will be wiped out, especially in small samples. And also we did a distance correction. So Tobin et al. 2020 uses the Gaia data to determine the distance to each protostar. And instead of assuming a common distance of 400 PC, we use the distance from Tobin. And this will improve the mass estimate by around 10%. So it's a minor correction. So now go on to the outflow mass ejection rate. So currently, what the people do is they use the outflow length divide by the outflow velocity to estimate the outflow timescale. So, and then they use this timescale. They measure the mass of the outflow and then divide by this timescale to get the rate, the mass ejection rate. The problem with that is, how do you determine the outflow length? For example, this is very observation dependent. For example, on the image on the left, you can see the outflow length is cut off by the field of view. And how do you determine the characteristic velocity for that outflow? The outflow wind, it's a spectrum. It moves in different velocity. How do you assign a single velocity for the outflow? So this has caused a big problem. If you look at the recent large surveys have been finding conflicting results, like outflow mass and momentum injection rate decreases between class 0 and class 1. This is a finding by Apex in 2016, and you have a mass and momentum injection rate that is independent with evolutionary stage. So this is by Fredrickson et al. 2020. So these two surveys are big surveys, 40 or 50 protostars, but they're still finding conflicting results. So why is that? The problem lies in the method. So if we use the outflow length to divide by the outflow velocity to estimate the outflow timescale, you are basically assuming that the molecular gas inside the outflows move from the source to the current position in a uniform velocity. So this is a very bad assumption because most of the outflow gas are entrained gas. They are not directly ejected from the central protostellar disk. They are pushed away by high velocity jets. So they do not travel from the center of the protostar to its current position, not to mention in uniform velocity. So this is a very bad assumption. So inspired by Botans et al. 1996, we invented a new method. So the idea is to use a ring mask to estimate the outflow rate. So for each channel, we use the width of the ring divide by the velocity channel, subtract the system velocity. That gives you the relative velocity of in that channel. And this will give you the crossing time for that channel. So we compute the mass spectrum we divide the mass spectrum with the rate, the crossing time. And this will give you the outflow mass ejection rate without dependence on the outflow length and the selection of outflow velocity. So we can do this by, we can change the radius of the ring to obtain the mass ejection rate profile. So by averaging over all the sources, we found the class 0 sources have mass ejection rate a factor of 2 larger than the class 1, and it is a factor of 2 larger than flex spectrum sources. As for the momentum ejection rate, the class 0 is a factor of 7 larger than the class 1. And for the energy ejection rate, the class 0 clearly dominates over class 1 and flat spectrum sources. So Dahan et al. 2015 measured the time scale for different classes, and adopting that, we can find the mass loss rate doing class 0, class 1, and flex spectrum phase. So we found at the end of the flex spectrum phase, we expect a typical outflow to remove around 2 to 4 solar mass of mass from the source. And as for the momentum, at the end of the class flat, we expect the typical outflow to eject around 12 to 25 solar mass kilometers per second of momentum to the core. As for the energy, most of the energy are ejected in the class 0 phase. And class 0 phase, the energy is around 100 times larger than class 1 and flat spectrum phase. And around 3 to 6 10 to the power 45 erg of energy is injected into the core by the end of class flat. So, okay, moving on. Now we created the ring method. We can generalize it, make into a generalized ring method. So the idea is, instead of creating the ring, now we can view each pixel as a thin ring to estimate the instantaneous rate. So the method is very similar to what I described with the ring method, But the main difference is now we obtain the mass spectrum for each pixel. And for each channel, we compute the crossing time by using the pixel width to divide by the velocity channel, subtract the system velocity. So with this, we can now create the first instantaneous mass, momentum, energy ejection rate maps. So here is just some examples. And with this 2D maps, we can start to do some very interesting statistics. So now this brings me to the second topic. Understand the outflow core interactions and its implications on core collapse. So we start from a traditional way. The people usually, when measure the outflow core interactions, people look at the opening angles. So it determines how the opening determines how much materials are affected by the outflow. So we follow the Dalham et al. In prep method. This method was first discussed in Offenen et al. 2011. So we create a CO mask from integrated intensity map, and then we record number of pixels for every angle and fit the Gaussian. And this will give us the half opening angle. So we found the opening angle increases with time. And however, we want to do more than that. So not just the opening angle, we want to understand the angular profile of outflow energy and momentum. So, so we start with creating a line mask. So with one side 1, the other side 0, this mask is just to separate out the blue shifted and red shifted outflow. And we applied it on the 2D momentum map. And we calculate the position angle for each pixels, and we can find the outflow momentum as a function of position angle. So this is the angular profile of outflow momentum. So we averaged all the sources. So here shows on the left shows the angular profile of outflow momentum. On the right shows the angular profile of outflow energy. So this is the top row is class 0, then followed by class 1 and flat spectrum sources. So this is very interesting. Just look at this. You can see the class 0 outflow is very concentrated on the outflow direction. It's very collimated. And in class 1, you can start to see it's very spread out. Oh, the red and blue line represents the red shifted and blue shifted outflow lobe. So this is average for all the sources in class 0, class 1, and flat. And for the flat spectrum sources, the profile is a bit strange. You can see it's in a T shape. So we start to see some peaks at perpendicular to the outflow direction. Possibly it's due to inflow accretion. We still need to check on that. So we did the same for the rate spectrum, angular profile of the mass, energy, and momentum rate. So similarly, we found for class 0 source, the energy rate and momentum rate is very collimated. And when we move on to class 1, it becomes very spread out. And we also see some strange peaks perpendicular to the alpha direction for flat spectrum sources, possibly due to inflow accretion. And to have a better idea how it evolves, we invent new quantities called momentum opening angle and energy opening angle. So we plot the momentum and opening angle and energy opening angle as a function of bolometric temperature, which is an indicator of protostellar age. So we found both the momentum and energy opening angle increases over time. Similarly, the momentum rate opening angle and energy rate opening angle also increases over time. So just to compare between the traditional conventional opening angle with the momentum and energy opening angle, we did a simple linear line fit. So we found the slope of the outflow opening angle measured from the integrated intensity map to be a factor of 3 to 4 times smaller than the energy and momentum opening angle. So this means that the class 0 sources, for class 0 sources, the momentum and energy of the outflow are highly concentrated in collimated jets. So, and we want to argue that the evolution of the angular momentum of energy and momentum opening angle is more important than the traditional opening angle in determining how much core materials are impacted by outflow. So I want to put up my summary slide. So we look at a large scale, we look at the filament angular momentum. We found the first rotating filament at few thousand AU scale, and we measured its specific angular momentum. We found the specific angular momentum profile is consistent with the rotation acquired from ambient turbulence. Now, at the smaller scales, we look at the role of outflows on regulating the disk angular momentum. Outflows plays two roles. First one, outflows can directly remove the angular momentum from the disk, and it can also affect the accretion, a collapse of the protostellar core. This is injection of the angular momentum. So to explore these two aspects, we establish an accurate way to measure the mass loss rate of the outflows. We invented the new method, ring method, and the generalized ring method to measure the mass loss rate. And to have a better understanding of the outflow core interactions and its implications on core collapse, we invent new quantities: outflow momentum opening angle and energy opening angle. And we argue that evolution of these two, energy and momentum opening angle, is more important than the traditional opening angle in determining how much materials are impacted by the outflow. So together with these, we want to establish the role of outflows in determining how the evolution of the mass and angular momentum of the protostar disk system. So that's the end of my talk. I will take questions, and thank you.
So there is one question by Yancy in the chat. How does your core mass loss estimate during the embedded protostellar phases compare with the pre-stellar core mass distribution? Any evidence for core mass growth?
Core mass growth. Oh, so this is a topic we want to explore more. So we right now we first focus on the outflow. In the next phase of our project, we will start to measure the core mass from the C18O, 13CO, and CO. So later it's an ongoing research. So in the future, we want to link the core mass directly with the outflow and to see how outflow impacts on the core.
In your study of the rotating filament in Orion, I'm trying to picture how this filament is spinning around its axis. How does the angular velocity vary with radius? Is it a function of radius? It's not a solid body, I would imagine.
It is not a solid body, but it's quite close. So the solid body, so the VR is proportional to a power of 1.8. if it's a solid body, it will proportional to r to the power of 2. So so it's a between, it's close to a solid body. It's close to a solid body. So the theoretical profile set by turbulence is VR proportional to 1.5. So usually in observations, we will see the slope in between, usually r to the 0.7 or 8. So it's something, it's collapsing, and yeah, so it's collapsing, and the profile is consistent with the set by turbulence. Does that answer your question?
Roughly, yeah. So is there a turbulent effect which is producing slowing of the rotation in the outer parts of the filament?
Okay, so the main reason we think there's deviation from the profile set by turbulence, the R1.5. The main reason is because of the magnetic fields. So you have a rotating filament like this. Magnetic field is spreading in this direction. So even though we don't have like magnetic braking, if magnetic field is parallel to the rotating axis, you'll get the alpha waves transferring angular momentum out. So that will quickly slow down the rotation. But if magnetic field lines is this way, parallel to the rotating axis, there is still going to be twist, the rev up. So that is why it is in between the solid body rotation and the pure profile set by turbulence. And this is also why the filament is still stable. It is not, even though the gravitational energy dominates, it's not collapse into, it's not collapsing radially, because you have the support from the magnetic field lines. And because it's rotating, then there should be a twisting of magnetic field lines supporting the filaments.
Okay, so we have another question. Caitlin, would you like to ask a question?
Sure. Can you hear me okay?
Yeah.
Okay, great. So it was a really, really nice talk. I'm really excited by these recent Outflow results. But I do have one quick clarification question on sort of your statements about the expectations for disk radii as a function of age. And that's that I think it depends on whether you're talking about gas or dust. And I thought the Tobin result was, yes, there was some shrinking in the radii, but those were dust radii, right? Which could be consistent with radial drift and grain growth. And so I guess I'm wondering whether or not your outflow sort of momentum opening angle and energy opening angle constraints can help distinguish the explanation for shrinking disk radii, i.e. is it dust or is it likely the gas doing it as well?
Yeah, that's something very interesting to look at. So so we want to see whether outflows and impact on the cores, and then how it affects on the accretion of the materials, and which impacts the disk growth. So it's all well connected. So it's something to explore more. So in the future, when we look at the data for the cores, and we will try to see if there are any accretion streams and how it links to the outflows.
Okay, so next we have a question from Thomas Quinn.
Hi, that was a very thought-provoking talk. I just want to understand, where does the angular momentum of the filament come from?
So the angular momentum of the filament is mostly set by turbulence and also just the collapse of the cloud. So if you just have if you have the cloud collapsing, and it will generate the angular momentum, as well as also with the turbulence, general supersonic turbulence.
And that would, you would expect that to be, give angular momentum along the direction of the filament, not perpendicular to it?
That's a good question. We didn't really look into where does that angular momentum of that filament comes from the larger scales. It's the profile. We know the profile is set by turbulence and also the magnetic field lines. As I explained earlier, the twisting of the magnetic field lines also affect the profile. So if we want to look at how the initial angular momentum of the filament, we need to, yeah, that's something interesting to think about. I don't really have a clear answer.
I agree. It's something very interesting to think about. Thank you.
Is there any other question? Actually, I have a question. So, so I'm wondering if the higher UV environment, external radiation would actually affect the turbulence or any other parameters of your simulation, for instance. For instance, like not only that outflow, for instance, there could be disk outflow due to disk wind, but also enhanced by the external radiation field. So I'm wondering if you're considering that.
So for the radiation, for class 0 and class 1 sources, you have dense envelope. So it's well embedded inside the molecular cloud.
So you don't worry about that.
So you don't have strong radiation. So the main effect might be like cosmic rays might cause some ionization inside inside the deep dense region of the core, and cosmic rays can increase the ionization rate, so which will affect on the coupling with the magnetic fields. So that's something I can think of. But for radiation, because of the shielding of the protostatic cores, we don't expect much effect.
Okay, so if there is no other question, you can maybe, if you're in the Zoom, you can unmute and then thanks again for the speaker. And then we'll see you, well, not next week, next week is a Labor Day, so the week after. Okay, thank you.
Okay, thank you everyone for inviting me.
Now we stop recording.